knowledge is not like for a thing that we not explain, but Yunpeng Li, and you lecture at the university can explain much better what this really is. Methods are and introduction and also invitation. Yeah, so I was hopefully explain this differential particle filter and also in the beginning why this is a very interesting topic to me from my first experience as an engineering master student. Before that, I would like to acknowledge the contribution from some of my PhD students. Actually, Xiong Chen is my former PhD student and now a postdoc in my group working on medical AI. He's behind the majority of our work on differentiable particle filters and also has expertise on optimal transport methods. And he's on market for factory population. So if you know suitable population, so do let us know. And then Jiang Zhou, who is sitting here, so he's a first-year PhD student, already made significant contribution on our work on regime learning, differential particle filter, and also he's planning to release a code base soon. Well, I'm saying this in public to give you some more motivation operation. So that is very much helpful. So the structure of the talk today, so in the first session, I will again have a gentle introduction to particle filter and also talk about parameter estimation, and that leads to the introduction of differential particle filter. I will talk about those different components, actually not limited to differential particle filter, but particle filtering essential components and how we can use neural networks to construct them. So the idea is to really have a data adaptive approach for us to construct particle filters for real world. And then that would some summary and future direction. At any point, if you have any question, let me know. So this will be pretty much, I would say, let's say applied piece of work, and also question will be welcome. But I would like to be more informed. And also disclaimer, this is not an exhaustive survey. The talk is pretty much based on a survey paper that Xiong wrote that published at the Foundation of Data Science this year. However, this one will just cover a subset of the topics discussed in the survey paper, and also even the survey paper, I wouldn't say it's really that exhaustive. So I will start about why I became interested in this area, differential particle filter, from some of the work I did 14 or 13 years ago when I was a master student. At that time, so basically the picture taken here was taken at McGill University in Montreal. So I was an exchange student at that time. And the application we are working on is something called device-free target tracking. So here on each pole, there's a sensor mounted there, so Zigbee sensor that can transmit wireless signals. And then there are 24 of those sensors as shown in those circles here. And this poor guy, Rizwan, my former lab mate, he will just walk inside this area. And you know that when we are walking inside the area and there are wireless, let's say, sensors around the transmit signal, we will cause an attenuation to the signal strength. And then the topic here, the task here, is to use the change of the received signal strength between those pairwise sensor links to infer where the people are. So here you can see that, well, there are two people here, and then those, let's say, dashed lines are the true trajectory, and then those, let's say, boxes are our particle estimation. At that time, that was the first time I learned about particle filter. I really did not understand much about the principle there. So it's just so amazing to me that such a simple algorithm, basically, initially we were implementing just a bootstrap particle filter that can work well. Although right now I say it works well, it took me probably between 3 months to 6 months to figure out how to construct those different components of particle filters. How people move, so what is the standard deviation, and also crucially, what is the non-linear relationship between the target position and also the sensor measurements of those links. Because you can, without us even writing down the equation, you can see that this is pretty much let's say, non-linear and non-Gaussian because I'm standing here, and for some links between sensors here and there, that change of the signal strength will not be linear with respect to the, let's say, my position here. So because I spent months to work out how to estimate a few parameters in those models, I really have that idea how we can do this more efficiently. And then just 5 years ago, so just before pandemic, I know about this differential particle filter. That's why we quickly start to work on that. And then a little bit more motivation. This is actually rather, I would say, simple real-world example. Let's look at something more interesting. In autonomous driving, well, there are a number of sensors in each vehicle there. So radar, LiDAR, camera, and also there are a number of targets, so pedestrian, cyclists, and also vehicles. So we are really looking at complex scenario and also complex dynamic measurements. To handcraft those features, like what we did in this example, is basically impossible. So I can also basically reveal before we go into the detail later on that we were only estimating 3 parameters there because it's just that we are only able to do that analytically for those 3 parameters. And here there's so much more on how we can deal with that. Okay, so before we go to those technical detail differential particle filters, so I would like to introduce, let's say, the background. So state space model, we have seen it in many times this week. So just probably the only thing new here is, well, I use S to denote the states because some of the initial seminal work in differential particle filter were done by people in robotics. We can check those people on the ground floor working on robotics, whether they typically use S to denote states, and then use O to denote the observation, and then T just time index that we often use. And for dynamic model, we can have a density. So if density is available, so we can use P theta of ST given ST minus 1 to denote that. And then also there can be a functional form. ST is equal to some functions of KT, capital KT of the state as a previous time step. UT is a noise variable, and theta is just a form. And in differential particle filter, actually, this is a form that is more commonly. Then for the measurement model, we want to have access to this likelihood so we can evaluate the weights, importance weights. But also, we can also have similarly have a functional form shown like this using capital HT. And then our goal for particle filter is that we assume that we know the dynamic model and the measurement model, how we can either approximate or obtain this marginal posterior or joint posterior. And there are different ways to do that. So in the nice linear Gaussian world, Victor has explained that Kalman filter is really the optimal filter, and also along with a few other speakers. And then for non-linear, non-Gaussian scenario, particle filters are really useful there. So I will not dive into Kalman filter. There are already a number of topics here, but I will quickly talk about the particle filter. Well, one thing is really to talk about, let's say, the notation for you to be familiar with a new notation we have here. But also, second thing is that I learned some Latin from Petra on Monday. So repetitio est mater studiorum. I cannot believe I spoke Latin in public just now, but this means repetition is the mother of learning. So having the same contents from another slightly different perspective, hopefully can also be useful. Well, what is particle filter? Well, for boost particle filter, the very first particle filter I implemented more than a decade ago. I don't understand how this can work, but it's really simple, right? So we have a set of particles, so N particles. So here they are, let's say, we use those green particle clouds to represent those N particles to approximate the posterior time step T minus 1. And we can propagate those particles using the dynamic model. And then you can see the particle clouds are slightly different color, but they become bigger because we inject noise in the dynamic model. And then in this bearing only example, basically the sensor will receive the direction. So we'll basically report the direction of the target. So that is why you see that all of the particles, the new particles along this direction will have higher, let's say, density. They are shown in this heat map as red here. And we use that likelihood to conditional likelihood to represent the weights, and we resample based on the likelihood. So that is how simple it is. Okay. I don't think we have any question here. And then the question is that, well, why this Monte Carlo sampling, or why this updating procedure, simple one, makes sense. So very quickly, why do we do Monte Carlo? Well, because we want to have access to some target distribution, but often they are not analytically tractable. So we draw samples there. So we use a set of NP Monte Carlo sample to represent this target distribution. And then for us to evaluate the mean of some utility function, so U of S, so S is distributed according to this P, we can basically write it down using the definition of expectation, and then plug in this empirical approximation and get this empirical mean. And very simple. Well, often, as we have learned, so we cannot directly sample from that P because, well, we don't know what the P really looks like. So we sample from some, let's say, easy to use distribution, so density Q here. And then if we want to evaluate that same expectation again, so we basically can just multiply or divide, and also divide this QS because we will cancel it out. And then instead of drawing samples from P, we draw samples from QS. And then naturally, if we want to evaluate the same expectation, then we basically need to weight those particles according to the ratio between the target distribution P and the proposed distribution you use to draw samples. And then if we do the same thing, it just means that to evaluate the mean, we need to evaluate the utility function U on those samples drawn from the proposed distribution, but then weighted them according to the ratio. And there's quite some talk from Denise on Monday that we also can have self-normalized importance weights there. So basically, this weighting can be done by finding some importance weights proportional to the ratio between the target density and also proposed density, while ensuring that those weights involve. Very simple thing. And how is that related to particle filters? Well, here just that, well, we basically use those weighted samples, so drawn from the proposed density Q, and then with those weights to approximate our target distribution here. Here I will just quickly show the sequential importance sampling. So we would like to have access to this P, so joint posterior P of S from S1, S2 up to ST. So I did this using S1 to T, given all of the past observation of 1 per T. And then the first one is essentially the definition of the additional density. And then we go on, and then basically expand the numerator using the definition of the joint density. Expand the first term again. And then we can quickly see that this first term becomes a posterior at the previous time step. And then everything we are talking about, the Bayesian filtering, is recursive, let's say, Bayesian inference, which means that we can write it down as the posterior as the time step T is proportional to the posterior as the previous time step multiplied by this density obtained through your dynamic model, and then this conditional likelihood. So very simple on this. Why this matter? Well, if we can draw samples from some proposed distribution Q, and this Q we can factorize it like this, which essentially what we did with bootstrap particle filters, well, proposed really more than 3 decades ago. Then using that importance weighting, importance sampling mechanism, we can evaluate that this weights, importance weights, has to be proportional, well, according to this ratio, so the density of the posterior divided by the density of the proposal. and they are proportional as we showed there. And then the first two terms in the numerator and denominator basically cancel out with each other. So that is why we are left with a likelihood. So very simple on that, but it took me from engineering point of view, engineering master student. So you first implement this, so it's very useful to know why this makes sense. But if we sample from a general density Q, then we have to modify that importance weight computation formula slightly, so that again we have that WTI equal to the ratio, and then we just plug in the formula we obtain here. So from here, and also the Q from basically from here, and then we can see that the first term in the numerator and denominator becomes unnormalized importance weight in the previous time step, and then this ratio, so the dynamic model, the condition likelihood divided by the density of the proposal is what we call incremental weight. So in each step, we only need to update this part, we'll compute this part and multiply by multiply to the unnormalized importance weight or normalized importance weight to get the new weight, and we normalize it to get the self-normalized importance weight. And then in terms of the procedure, so again, very simple to do. So basically, we first draw NP samples from the prior distribution and then set all of the particles weights to be equal. And then we just need to draw samples from the dynamic model or the proposal distribution and then update the importance weights like this, and then compute the normalized importance weight. And then that is how the sequential importance sampling mechanism work. And also we have a lot of discussion on Monday why there's an issue there. So that is why we need to do something called resampling. I think there are different interpretation on why resampling is good or bad in different scenarios. We also discussed that on Monday. I think that the good part is that it really increase the, let's say, reduce the variance of your estimation as a current time step, because you throw away those samples that have very small weights. But indeed, this also inject noise in the path because you throw away many of the path trajectories. So basically, as T increases, the variance of WTI tends to increase. So just bear in mind the importance weights we compute here is the importance weights of the trajectory. So from either S0 or S1, so depending on where you start, up to the very last time step, the latest time step. So that is why the variance tends to increase. So I also treat it this way, consider it this way. So basically this importance weight or the log of the importance weight is the sum of the log of the likelihood ratio. And you basically add more and more random variable there because and then that when you add more and more random variable there, then the variance will increase. And if you take the exponential, then there will only be a few samples with big weights after you perform the normalization. So that is why this is something that we should do. So in terms of resampling, to reset the approximation to reduce the particles and multiply those with high weights. And those what we call, let's say, in terms of conceptually, what resampling is. But I want to dig a little bit deeper here in terms of how we actually perform resampling, because this has consequences you will see later when we incorporate neural networks into particle filters. So there are different resampling schemes. So for example, there's multimodal, multinomial resampling. So basically, well, initially we have those samples. So P hat of S1 to ST given O1 to OT represented by those S1, S2 up to ST of the NP samples, each with a normalized importance weight W tilde TI. And our objective is to gain a new set of sample, so S tilde 1 to S tilde to S tilde and TI, and those have the equal importance weight, and then they should basically very close to each other. How can we do that? Well, from the name of the multinomial resampling, you can perhaps guess that there's something to do with a multinomial distribution. So you can essentially write down this formula using this one. So instead of using S tilde 1 to T I to represent the new sample, we can actually use the old, let's say, the samples before resampling to write it. So we again have the old original samples, but just that whether those samples survive or die, or let's say multiply, copied, depend on this Ni, and this Ni are drawn from multinomial distribution with the parameters decided by the normalized importance weight. And you just draw from this multinomial distribution NP times, and you get those N1, N2, and NP. So if those are N1 is equal to 0, just means that sample died. Okay. So conceptually, this is easy. But actually, how this is done? So we cannot just tell, well, right now what we do is just tell the computer generate that, but how do we generate those samples? Well, we generate this, well, in terms of those simple distribution using inverse cumulative distribution function. So what we do is that, well, we introduce a few those, let's say I call thresholds. So C0, C1, C2. So C0 is set to 0. C1 is just equal to the weight for the first particle. So W tilde T1, and C2 will be just a sum of the weights of the first two samples, and then so on. And then after you generate those C, so for all of those NP particles, and you basically form interval there. And then you can just create those NP uniform samples and then find which interval those uniform samples are. And quickly we can see, well, if for one particular particle, the weights are high. So for example, for the third particle, the weight is very high, 0.9. And then this gap of this interval is very big, right? So if you draw uniform samples between 0 and 1, it is very likely that this UI will be landed in this area. And that just means that, well, that sample will survive. And that is how we do it here. If we look at from this picture, well, we can first, after we obtain the normalized importance weight, we can compute those C0, which is equal to 0, C1 equal to the importance weight of, let's say, the first particle, and C2 and C3 up to the final one, which is 1, because this is a cumulative distribution function. And then we can basically draw a sample. So if this weight for the second particle is very large, as I said, 0.9 or 0.95, this one will have cover a huge area. So if you draw those uniform samples there, most sample will be there. And then this is inverse CDF function because it maps from, let's say, what you get from those, let's say, samples to the particle index we have here. And also you can quickly notice that this is a discrete function, right? Because, well, you just have those discrete particle index there. And that brings some problem that I will touch upon in the second session today. Now, this makes the resampling process non-differentiable. That is a problem when we want to incorporate neural network there and then perform optimization. Is this clear? Okay. So basically, with resampling, so particle with high weights often copy multiple times, and then with low weights, they will die. And also, when I first see this, I will say, well, wait a minute. So this really depends on the uniform samples that we draw here. And then this can also really lead to lots of unexpected scenario, and that we call high variance. How can we reduce variance? So there are different approaches to do that. For example, we can have residual resampling. For example, if we think about the scenario I just talked about, if we have a particle with weight 0.9, we really want to avoid a situation, unfortunately, with those random sampling, only a few samples land in this area with high weight. Although it's quite unlikely, this can happen. So what is this residual resampling does is to have a combination of deterministic resampling and also those random resampling there. So if the importance weight is really high, so we basically make sure that a large number of samples will be copied there from that particle, and only a small amount of the residue of the importance weight will be used to generate the multinomial samples. So just to reduce the number of, let's say, those unexpected scenario. Similarly, stratified resampling, essentially, instead of drawing uniform samples from 0 to 1, it will draw samples from those smaller intervals. For example, for the first sample, it will draw, if we are resample, let's say 10, or let's say if we want to generate another 100 samples, it will first generate a uniformly distributed sample from the interval between 0 and 0.01. And so that there's one sample there, and then for the next interval, you generate another sample. So just to make sure that those samples are really more evenly distributed. And this systematic resampling does basically almost the same thing, but you actually even make sure that the space between those uniformly drawn samples are even more even for those adjacent samples. I won't go into the details there, but then the take-home message there is that all of those variants of resampling methods, they are implemented through variants of the inverse CDF. And what was the issue I talked about just now with those inverse CDF-based resampling methods?
Continuity.
Yeah, so continuity, and then there's no continuity there, so it's not differentiable. So those are the common problems. And then also we want to have a way to assess the quality of the proposal distribution. And so we can use effective sample size, which essentially target, well, one effective sample size, the definition I would say, well, Victor knows this so much better than me, but then basically this is about the number of samples that if we directly generate from the perfect, let's say, target distribution, we propose the perfect Monte Carlo sampling, as Dennis put it, how many samples we need so that we can obtain the same variance as those using those samples generated through those important samples or particles here. So the different ways to compute that, one simple way or very popular ways to use this formula to compute that, but also there are scenarios that this may not work well. However, we just adopt this criterion for us to define this sequential importance sampling. So the first step is again drawing samples from the prior distribution P0 of S, and then we can basically set the samples within the weights are just equal, and then we perform the same sequential importance sampling step, but then just in the end we can check the ESS threshold and then see whether we need to perform resampling or not. As I just said, so in some situation, you don't want to frequently perform resampling because it indeed introduces the noise. So there's a balance there. And so after we have introduced, let's say, more general proposal distribution, so we can update this set of diagrams. So instead of propagate your samples using the dynamic model, so you can propagate your samples using the proposal distribution, where you need to update your weights accordingly and then resample based on your updated importance weights. So that all in that way we're familiar with. I think I'm done there. And then for parameter estimation in particle filtering, again, we'll just go through a few concepts. I will just dig deeper into the online EM algorithm because I think after Victor's, well, during Victor's talk, there are some questions about how the EM algorithm is used and also whether it can be used in the online setting. So essentially what we have here is that most state-space models depend on some parameter theta. And then we assume that the data corresponding to some two parameters are generated. And even if this assumption is true, can we learn those theta star, the true parameters from data? There are some simple scenarios, so let's as an engineer, I would like to look at the, let's say, real world example, although this is a numeric example. So for that, bearing only a target tracking model that we use to generate the graph. Well, the dynamic model is basically ST equal to ST minus 1 plus UT. And then UT is a Gaussian random variable with parameter sigma S there. And then this AT is just an angle. And then with this, well, it's again, there's an additive Gaussian noise. So in this case, the parameters, there are two parameters, right? So sigma S and also sigma O. And then for stochastic volatility model, well, we have a little bit more parameters. So we have this eta, mu, delta for the dynamic model, and then this basic gamma there in the likelihood, so in the measurement model. And then those are the parameters we want to estimate. Whether we can do that. I will touch upon that later, but just to introduce what we mean by parameter here. And then, well, we have talked about number of times, so how we can do that. Well, in machine learning, we often basically maximize the data likelihood. And then for particle filter, we can do the same thing. The tricky bit is that the data likelihood we are targeting increase over time. So theta, basically we have the data likelihood, which is a function of our observation from all of the past time steps. And then to obtain this, well, we can basically treat this data likelihood as a margin of the joint posterior, not joint posterior, joint density, sorry, joint density of the state and observation in all of the past time steps. And then we can basically factorize it using the conditional likelihood and also the prior. And then with the EM algorithm, we basically perform iterating those two steps. In the expectation step, we assume that we have some, in the past iteration, we have some theta, no matter how good it is, we have some theta there. So we can perform particle filtering, so obtain those state. And we can use that state, those state estimation or approximation to perform this expectation of this log joint density. And then after we obtain this, we can basically maximize this Q with respect to the parameter theta here. And then we use that as our the parameter estimation in the next iteration. So this is basically essentially what Victor has talked about. Well, to just avoid the issue that the dimension always increases, so we can basically just split the data into different blocks. And then, so in this case, we can have, let's say, n blocks, and each block have the length L, capital L. And then basically the log data likelihood can be split into the sum of those log likelihood in those different blocks, and we call it, let's say, log pseudo likelihood. Because this is not the real likelihood, we are just looking at the data likelihood among each block of observations. And then for this one, it's just basically the same procedure, but just we focus on a finite, let's say, number of those, not finite, but just fixed number of the observation and also states. In practice, online EM basically computes a set of sufficient statistics to compute Q and perform maximization. But what does that do? Basically, what does that mean? Well, I'll go back to the same example I introduced in the beginning, that radio frequency tomographic tracking example that I introduced in the beginning. So in this one, we basically can have a dynamic model that is quite simple. It's an autoregressive model. So this alpha just can be some value very close to 1, slightly smaller than 1. So to make sure that we have a stationary distribution, so we can use the online EM algorithm to perform parameter estimation. And then there's one parameter, sigma u, so the standard deviation in the dynamic model that we can estimate. And then to construct this form, because when you do, let's say, conduct some, let's say, more practical research or experiments, well, what you receive are just those OT. That's everything you have. Those received, actually not even the change of the received signal strength, but just the received signal strength. What is the relationship between that OT and your state ST? well, and then basically what we do is to use those plunger. So you see there's some interesting plunger there that basically mark where people are in different places. And then what we do at that time is that when I or this one or another person go into some places, so touch on that plunger, and then we just use a stopwatch or not use a watch to record the time. And that is how we infer the ground truth. And you can see that this is a really slow process for us to get those ST, so the latent variable. And the reason we want to obtain those ST is that if we obtain those ST, we know, okay, at time step T, what is a state value, and we know what is a OT, so the value the observation value, then we can see what is the functional form, what is a functional form of ST of OT with respect to ST. So we kind of find that this exponential function makes sense there, but then there's some unknown parameters, so we put a coefficient there, and also there's another parameter there, sigma O, and plus some, let's say, Gaussian noise with another parameter there. So I basically talk about 4 parameters in this example. So sigma U, sigma S, sigma O, and V. And we actually can only estimate 3 of them. So this B, sigma S, and sigma U, not this sigma O. The reason for that is if we want to perform this step, so basically perform this maximization step, we need to be able to really compute a set of sufficient statistics to perform that maximization. And this really requires that if we want to perform online EM, so the distribution family has to be, well, in the natural exponential family, in that family. And then, but if we consider the form we have here, so sigma O really has some nonlinear relationship between, so basically you cannot, if we treat this sigma O as your part of your theta, this cannot be written within that natural exponential family. And then just means that we cannot write down that sufficient statistics for us to compute optimization. So the difficult part is that, well, even for this simple example, we can only estimate 3 parameters. So you have to set this sigma O by hand by doing experiments. And also to find this functional form, this handcrafted form, really can take months. The difficult part is not about we're looking at the data and then find this relationship. The difficult part is that well, it takes so much time to conduct the experiments, find the ground truth, and then do the post-processing. And it's just a very controlled experiment. And this will be so much more complicated for more real-world examples. Okay, so this is just one type of parameter estimation technique. So for maximum likelihood estimation, we can also do Bayesian estimation. I'm sure that later we are going to have more discussion with those methods. So you can use MCMC and also other methods. So they can be effective, as I just said. So this one, we actually have very good performance to perform online state inference and also parameter estimation in some real world examples. But then this often assume that the structure of the dynamic model and measurement model are known. So basically, we assume that we know this, although we really learn those from data just by analyzing the data. And also we know part of the parameters, for example, that sigma O is known. So this is really restrictive. And that is why when I learned about this differential particle filter in 2019 from some companies that work on real world data, this looks so interesting. So why is this interesting? Well, just now we saw some, there's a control environment. Let's look at the real world scenario. For autonomous driving, so if we, let's say for Tesla, look at images. So for each image, so this is your observation at one time step. You can also have multiple time steps. How can we construct that functional form from your state? And your state can be not just about the position of the vehicle, but also the velocities and also driver's intention. How can that be mapped to this image. Well, what is a distribution? What is a nonlinear relationship? And perhaps for this car, it has a, for this type of sensor, it has one form. For another car, another sensor is another form. And think about the number of devices in the world, connected devices. We really cannot handcraft those models. And those are the questions that we have. So, and also even if we know, let's say for dynamic model, what is the distribution family to use? How can we optimize that distribution parameter? Because for that online EM example, for the homographic tracking, well, we need to really derive by hand what is the update formula to perform that maximization step. Well, for those more complex scenarios, how can we perform this optimization? And that is unknown. And for the minimum model, again, how to measure or model that relationship between observation and hidden states. And also something I didn't touch upon, but then also how can we, let's say, design the proposal distribution so that we can use information from the observation and in those complex scenarios, really to move particles into places close to the posterior so that it can work well in practice. Those are the questions there. It looks like differential particle filter is an interesting direction. And then basic ideas of differential particle filter is basically to incorporate deep learning tools, mostly neural networks, into the particle filter to build components of particle filter that we introduced in the beginning. So those different parts with neural networks, and then we can optimize. We also construct them in a way that we can optimize those components by gradient descent. And what are those components? So I put it here. So for the dynamic model and measurement model and proposal distribution, they can be built with neural network, and that's often the strategy to use unless the parametric form of those density or models are directly available. For example, for those stochastic volatility model. For resampling, it can be built with neural network, but also we can use other techniques that I will also introduce in the hopefully the second half of the talk. I'm really speaking probably ahead of my schedule. Well, what is differentiable? Probably I don't need to talk about that. Well, those are differentiable functions, but also there are some functions, although they look non-differentiable. For example, the popular ReLU function, they are just non-differentiable at finite points. And then for deep learning model, this is fine, because well, those happens, let's say, rarely in those finite points, and then you can basically approximate those gradients in a way that will not affect the final performance. But also there are other non-differentiable operations. For example, stochastic output. If the function is that we draw a sample Y from a Gaussian with mean X, and covariance is just an identity function. So what is just an identity matrix? What is a gradient of Y with respect to X? 0. Any other guess?
1.
1. So Y is 1.
Because Y is X plus noise.
Yeah, X plus noise. So very good, because we can use basically use the definition of the gradient, right? So EY dx. So we write it this way. However, if Y is X plus noise, so we need to evaluate the gradient using 2 points. So Y somewhere close to this X0 and also X0. So Y0 at point X0, because it's sampling. So those can be different epsilon, right? When you generate stochastic output, so Y is drawn from a distribution. So this can be from, you can have different epsilon. Well, the trick here, something we perhaps all of us know, is reprioritization trick. So you basically assume that error term, so epsilon, is just shared across those 2 points. So essentially you draw that sample epsilon first, that is not related to your X0, and then you just share that epsilon for both Y and Y0, and that term cancel out. So you basically have Y plus epsilon minus Y0 minus epsilon, so that one cancels out. So you have X minus X0 divided by x minus x0, which gives the answer one that Pierre mentioned. So although it's year defined, but there are different ways in using deep learning to address that issue. So this looks very simple here, but we will see that we use this trick throughout in differentiable particle filters. Is this clear? Any question? Yeah, I think I have more example later on to discuss this, so we can go back there if we did. And then stochastic components in particle filters. So basically we have those components include sampling from the dynamic model. So this is sampling. And it's also from the dynamic model and from the proposal distribution and also resampling. So the first two are actually very easy to deal with because we can use that same reprioritization trick to deal with the sampling and get gradients that we want. For resampling, it's a little bit trickier. So that is why it's still an active research direction. And then for different particle filter, all components need to be differentiable. And then here, just for notation, we use theta to denote the parameters of the dynamic model and measurement model. And then we use phi to denote this parameter in the proposal distribution. So this is just for notation, but you can also merge them together. I think the idea that you don't have to construct proposal distribution using neural networks, you can use the classic techniques to do that. Although there are also potential benefits we do this. So we construct proposal using neural networks. We will see examples later. And essentially, for differential particle filter, we need to construct that loss function. And then once we construct a loss function, there are different ways to do that. And we can just optimize it using gradient descent. And then there are really different ways to construct that. So in that online EM example, the very toy real world example, that loss function we use basically by hand, looking at the shape, plot the data according to the ground truth that we infer through using the watch, is basically to basically our eyes by looking at the basically the L2 distance between the distribution as the loss function, although we are not using gradient descent to do that. But to use this, to train differential particle filter, we need to have some more cleverly designed loss function. So I'm now going to go to the different components. So for example, the first one is the dynamic model. How can we construct differentiable dynamic model? So basically, this is a structure using the seminal paper, differential particle filter from 2018. Well, the reference I think in the next slide. So basically, as I said, so it was initially proposed by the robotic community because we really want to use, let's say, sequential Bayesian inference techniques in real world examples. So they have robots there, and for robots, they often have this AT, the action variable there. But for us, it's basically optional. You can treat this as just a known input. So you have an optional input here, and then you have another part of your input to this neural network is your state as a previous time step. At time step t-1, and then for the ith particle. So that is your input to the neural network. And what you want to get is a state as a next time step. So that is your dynamic model, right? STI. And then where is the noise added? Well, we just put it in a general form. So you have this epsilon I there. Really, there are flexible ways to inject noise there. You can inject noise to this AT, so the action. You can inject noise to those ST-1I. You can inject noise into the neural network parameters of different layers, or inject noise into the output. And then they have different consequences. And then I will also talk about that later. But just let's say on a high level, if you're injecting the output layer, that's often the easiest one. Because if you get this noise, well, sample noise from some simple, let's say, Gaussian distribution, it just means that the whole dynamic model is additive Gaussian. It just means that it's very easy to evaluate the density, although that means that your dynamic model is restricted to Gaussian family. But if you inject it here, with all of the nonlinear operation you will go through from neural networks, you will have, let's say, more flexible, let's say, distribution in the end for your dynamic model. But think about what is a downside of that for some arbitrary neural networks. You inject noise for, let's say, to this state, and then you propagate the noisy state or the action through a complex, let's say, arbitrary standard neural network. What will be the distribution of this STI? Well, we don't know, right? Because there are so many nonlinear operations there, unless the neural network has some special structure. So those are the different things we need to deal with. And also that is actually the reason behind the first few differential particle filter all have the bootstrap particle filter structure. Because what is the benefit of bootstrap particle filter? Besides it's simple, well, you don't need to evaluate the density of the dynamic model, because you only need to evaluate the likelihood to update the weights. So just something to mention.
The actions are fixed. Are you also learning the action model?
Yeah, so actions are fixed here in this context. I'm not a robotic person. I normally just ignore this. Any other question? Okay, so what the different options for this dynamic model? So the first option, the known parametric model, will, let's say, in cases, so in this stochastic volatility model, we already know the dynamic model, how this can be written, and you don't have to really, in this case, construct a neural network for this. You can basically write it down, and you can sample from it, and then you have those theta there, and then you can just optimize, and then that's it. And then this transition from ST-1 to ST is made differentiable through the replantation trick that I promised. So this will happen again. So basically, the state ST given ST-1, this is a Gaussian distribution, right? And to generate this Gaussian, what we can do is to, well, first write down the mean, so mu plus eta times ST-1 I minus mu, and then the noise term is just, you can just add beta times this noise term, and this noise term, so basically epsilon Ti, we can generate it from a distribution that is independent to any of your parameters. So for example, this can be just a standard normal Gaussian. So once you generate that, you treat it as just a known input. And then that is how you can make this non-differentiable process, a sampling process, differentiable, because the noise term eta Ti becomes a constant because you generated it. So for this iteration, it's as simple as that. And then the whole process, because that generation process, sampling process, independent of your parameter that you want to estimate, and then that is fine. Yeah, so I think this is heavily used in this auto-encoding variational Bayes paper, and recently gets the I think it's called what is the name? So I think in the iClear this year, so it will be shown as let's say the first iteration of the long impact award, because of many of the techniques from variational. Well, it used variational inference for us to learn for them to propose the variational autoencoder, but also the replantation trick is used there for the training of the network. And we are basically, yeah, we can use the same trick here. Sample from the distribution. Well, it's just basically essentially the same thing that I discussed. So we basically sample this as epsilon Ti from a standard normal distribution. And then we basically can write down STI in terms of this, and then this will be a differentiable function, right? Because we want to compute the gradient of mu, eta, or beta, and those are just a linear combination or the weighted. Well, it's just a function of those parameters with some known parameters. We basically get rid of this sampling process by directly sampling beforehand from a standard normal distribution. And the Monte Carlo estimation of the gradients is that, well, if you have NP samples, we can do this for each of the samples, and then this F theta is essentially that functional form. So neural networks or this parametric form, assuming that you have generated the, let's say, the error term independent of your parameters. So for each particle, you can generate a different, let's say, error term, because you don't want to reuse the same error term, just to reduce, let's say, the randomness from just getting one error term there. And we can just average them and to get the average gradient to approximate the real gradient. Option 2, as I just said, so for differential particle filter, you can have noisy action. So as we discussed, if the action is there, because action is available, so in a robotic scenario, so also, let's say, autonomous driving, so for example, turning the wheel, and when okay, this operation, this action has been done, so this is known, you can add noise to this action term, and then use that noisy action as an input to the neural networks to basically use that as an input to the neural networks, and then get your state. And then in this case, the particle density is intractable, as I mentioned in the beginning. So that makes it difficult if you want to use some general important sampling scheme. Then option 3 is to add noise to the output of the neural networks. So predict next state value without noise. So basically, here those are just original your state and also action. And then you move it according, while you perform those nonlinear transformations through neural networks, and then add it to your, let's say, so this is more like a ResNet type neural network. So you have your state in the previous time step as an input, and then plus some residue through the nonlinear transformation introduced from the neural networks. And then finally, you apply noise to the states by adding some, let's say, noise, so more likely Gaussian noise, multiplied by some parameter. And then in this case, you can indeed evaluate the density, or where the density is kind of restricted. And then finally, we can also use, not finally, but another option is to use normalizing flow. Well, here we denote the normalizing flow by P theta, so calligraphic P theta shown here. And essentially, this graph showing what we have talked about in the option 3. So basically add noise in the output of the neural network. So you basically propagate the state and actions through the neural network, and in the end, you add some noise there and get your noisy state. And when we talk about, okay, what is the problem there? Well, if this is Gaussian, you just have additive Gaussian distribution for a dynamic model. What we could do to make it more flexible, because in real world, not everything is Gaussian, is to add another layer of the normalizing flow over here. So this is conditional normalizing flow, which I will expand later. Actually, this is normalizing flow, using normalizing flow to generate a dynamic model. And so how many of you have heard about or know about normalizing flow before? Okay, not everyone, so I'm going to spend a little bit more time on this. Basically, normalizing flow is just one type of transformation, or transformation through neural networks. And then the special part is that this type of neural networks, the input to the output, this mapping is invertible. So it's a bijection. So for any different input, output will be different. For any different output, the input will be different. And we just construct this neural network through some, let's say, clever way through the architecture. So no matter what is the input and output, it will be invertible. How do we do that? Well, or why do we do that? Because if it is invertible, then we can just apply change of variable to evaluate the density. So P of y will be equal to P of x, and then multiplied by this inverse of the Jacobian determinant. So there are really different ways to construct the normal line flow, and that can really was a topic that we can discuss for hours. Here I just talk about a simple one called real MVP that also we adopt in some of our initial work on differential particle filter. So the way to construct this is to split your input. So here, let's say this is just a generic function. So input is X, output is Y. And then for the input X, we split the input into two parts. So the first, let's say, little d dimension, we call it X1, and then for the rest of the dimension, we call it X2. And then the output Y1 is a direct copy of the first d dimension of X1. So that's why Y1 is directly equal to X1. And the reason to do that is if there's anything different between, well, so right now, well, what is invertible transformation? So any different inputs will lead to different outputs. So if there's anything different within the first d dimension of the input, then of course you have a different output, right? Because this is a direct copy of the input to the output in those d dimension. And then for the rest of the dimension in the state X2, what it does is to, well, basically perform this transformation. So there's a C function there, which is a function of X1 multiplied by this X2 and then plus some T of X1. And it's just that we need to construct those C and T in a way that we ensure if all of the X1, so the first D dimension is the same, if there's anything different in the rest of the dimension, you will get different Y2. So by construction, you will have invertible transformation bijection. So that is a way to do that. And also going from the opposite direction, this needs to be the same. And the way to construct that for real MVP, if we look at in the mathematical form, is essentially, well, copy the first D dimension as I just discussed. And then for the rest of the capital D minus D dimension, what we do is that, well, we have an exponential operator outside of C. So this is essentially always a positive number. As I just said, so if we know that the first D dimension, there's anything different between the two input variables, and then we will have different output, right? But if the X1 to XD, they are the same, then it just means that this coefficient for XD plus 1 to D will be the same. But they will be the same and also always positive. So if there's anything different in the rest of the dimension for the input, they will lead to different outputs, right? Is that clear? Okay. Do we have, let's say, one example? So here. So basically, we want to show, let's say, for two different inputs. Let's say, I don't know if the audience can see that. So let's say we have, let's say, this X1 here, X2 here. If let's say the first, they are just, let's say, three dimensions, 0, 1, 3, and then this one is 1, 1, 1, 3. So this is X1, X2, or maybe I can put it as this way, the 4 dimension. And we split the state into two parts. So little d equal to 2. So to let's say those two parts just equally among those dimensions. And then for Y1, because it directly copy the first D dimension, so it will be 0, 1, and then plus some random, let's say not random, so some unknown value depending on the transformation C and T. But then for this Y2, just a different variable as output of X2, because it directly copy the first two dimensions of the state or the input, it'll be 1, 1, some unknown variables, some unknown variables. So of course, for different input, you will have different outputs, right? Maybe my drawing is too confusing. Okay,
Happen that the first two components of x and x1 and x2 are same, or
Yeah.
why is this not?
Yeah, so this is a simple case. So first two dimensions, they are different. And of course, you will always have different outputs, right? And if they are the same, then the first two dimensions of the output will be the same. And then now we perform this transformation. No matter what is the exact form, this exponential of C of the same input, because x1 to d, so x1 to 2, they are the same. So basically this coefficient is the same, right? No matter, so let's call this number 5. So this will be 5 times the rest of those two dimensions. And this is basically a dot product. Or let's say 5 and 0. So basically this will be the output of this function will have the same dimension of capital D minus D. So you can like an element-wise product. And because they are the same, if there's anything different between the other two dimensions, so for example, this one is 2 and 4, this one is 3 and 4. They are multiplied by the same coefficient. They are guaranteed to be different in the output. So that is why by construction, this will lead to invertible transformation. Okay. Any other question? Well, just one way to construct this, let's say, invertible transformation. Yes. Yes, that's a very good question. There are some conditions there, although yeah, this is very too restrictive, and particularly for this one. So that is why this is active research direction. There are different ways to do that. And it's just that this is a very simple form, and also it's very easy to evaluate the gradient here. It's basically a triangle, so we use it. I think this is just one initial exploration to adopt this form of normalizing flow and use it and show that it can work and solve a problem that we can have more flexible dynamic model. And there can be other forms that can be more flexible, can approximate more functions.
The answer is that this does have universal approximation, but you need infinitely wide layers, and a lot of them are infinitely many of them. But there are like other options, slightly more complicated, that can do it. I can get better approximations and less, like, not needing infinite layers.
Yeah, so there will be a trade-off all the time.
I have one.
Yeah.
So when you're doing it only once, right? You're not doing it like for every time.
Yeah, so here we basically it is more like amortized inference. So yes, we basically assume that those functional forms, their time, well, they do not depend on the time. Well, you can do that, but you don't have that many NSA samples to do the training. Yes.
And your loss function there would be
well, there are many different ways to do that. So that is one way to design the loss function, but there are also other ways to do it.
What's another example?
You mean another example of the training loss? Well, you can basically do individual training of those components of the dynamic model. You can also have end-to-end learning. So basically use your filtering results and compare with ground truth state estimation, if that is available. Or you can, so basically if we are doing independent or individual training of the dynamic model, we can just use ground truth of state to compare the dynamic model. So basically maximize that, let's say, density. But then if we can also just optimize the whole thing based on the filtering results. So that's just two different examples. We can also use, let's say, the maximum log latitude or the elbow of the maximum data log latitude. Different choices. I think it's going to be very interesting direction to see which one is more practical. But because there are so many different applications and we don't have a common data set and also task to do this, so we don't have a concrete idea, although right now we have some preferences of this loss function versus the other. And also it depends on what you have. And one thing that it's not so easy to have is the ground truth, so the state. So if we spend our time to get the ground truth, well, it just allow us to have more loss function available for training. But if we don't have the ground truth, we may have to settle down to things like log data like.
When you have multiple loss functions and you can't decide if it's something you decided on this multiple segment.
Well, right now we also, well, for semi-supervised learning, so if we have a combination of choices, we can also have the weighted sum of those times. I don't think that computation time right now is any concern there. It's really about what is the more effective in terms of target objective. Does that answer all of your questions? Okay. Any other question? Yes.
What are the restrictions to CNT? Does the code term have to be subjective at the right?
Yeah.
What are the restrictions to CNT?
I cannot think about on top of my head about that. Yeah, the paper, well, I shouldn't really say the paper says that. But because where you have the exponential one, I don't think there's a big restriction here. So basically, you need to map the dimension. Yeah, we'll be surprised if there's let's say, there will be very restrictive condition for those CNP because of the exponential operation there. But as this one is also not really the necessary one to enforce, let's say, this invertibility. It's just one convenient choice to use. Other question? No, then we can probably go to the other one. So other choice, so Peter mentioned about those regime switching particle filter scenario. So for example, if we think about, let's say, autonomous driving, the vehicles can have different states. So it can be, let's say, driving on the highway or stopping the traffic, or let's say just sitting there. So they are really different regime, and then that may justify different dynamic model. Can we really switch between those different regime and also make the model more interpretable? If we can tell, okay, which regime it is, and also we can do clustering, grouping, and those things can be useful. So we have done some, let's say, investigation. So Zhangjiu, we have recently our paper accepted at the Fusion. So to look at it, so besides the state and also observation, we can have the regime index. So assume that there are a number of regimes, so let's say 10 regime, which one to choose. And then there's also additional regime cache, which is just a feature vector that can encode information from the past regime. Because we don't just want to have the regime, let's say, taking the information from the past states, because the previous few states may also give you quite some information about where the target or state should be over the next few time steps. But also you don't want to have that over there, exceedingly long dependence there. So that is why, so Zhangjiu has taken inspiration from LSTM, so those RN type models to basically learn how much past states or past regime we should learn, and also how much past states we should forget. And then we can basically, that information can be used to guide this regime index. And also it's very hard to handcraft that dependence. So that is why we use the LSTM type structure to learn this dependency. So learn everything from the data. Okay, to summarize this, so how to build differentiable dynamic model. So we can add noise to deterministic function, so in different parts of the neural networks, and the sampling operation is made differentiable through the replacement trick. So, well, as we discussed, and can approximate the complex dynamics through different techniques. For example, normalized flow. Normalized flow is just one of the solutions that can be used here. So our initial, let's say, direction, but definitely there can be other things that you may find interesting to explore. And finally, we also have that regime switching type dynamics that we can we can. I think I will go through the differentiable proposal before we have a break, because this one is quite similar or close to the differentiable dynamic model, and the Mellman model and the resampling will look quite different, and that can take more time to explain. So differentiable proposal. So as I talked about, just now, so the normalizing flow-based differential particle filter, so they basically have the additive Gaussian noise on top of the neural network output, and then you add another layer of neural networks there, normalizing flow there to make the distribution more, let's say, flexible. But then just with that, well, how can we use, let's say, observation to guide where the particle really should go? Well, you can use a classic technique from particle filtering to construct the useful proposal, and that is actually an interesting direction to look at. But another quick thing, so if we go into this deep learning, let's say, field, we learn everything from neural networks, you can basically add another layer or another normalizing flow there on top of the output we get from the previous normalizing flow output. And then we call this conditional normalized flow. And I will explain why this is called conditional normalized flow. So basically, we first have this E theta and to construct flexible dynamic model. And then we can use a conditional normalized flow to construct flexible proposal. And this is what we have seen just now. So this is just a standard. So we call it coupling layer for normalizing flow. You have X1, X2. So split your state into different parts and then perform this construction. But it really doesn't use any of the observation. So if we think about the particle filtering context, so what we can do, this is something very simple that Xiongje think about is that we can use observation as one of the parameters or one set of parameters for this C and T. I think just now there are a good question asked about this C and T, but O can be used as an input of the C and T, because there's not many restrictions about the function form of, there are function restrictions. So for example, exponential can be a good one, but O can be used there. So in this way, the observation have been used was to construct the proposal distribution, because then we can generate samples. So Y1 and Y2 means samples we generate from this conditional normalized flow network. So just to compare them, so it's very, let's say, simple chain. Instead of just having the first D dimension of X as an input of this C function, we can have the combination of the first D dimension and O observation as an input of this C function. And similarly for this T function. And in that way, we use the information for the final capital D minus little d dimension. Although you can see the restriction here, it really does not affect how the first little d dimension of states are used. So this may justify other type of normalized flow being used here. And again, so very similar to the standard coupling layer of the standard normalizing flow, we basically can still have the invertible transformation. I will also have the triangular Jacobian matrix, so we can evaluate the determinant of the Jacobian very easily. And then the final piece of work, so another option is to have mixture of Gaussian. So that is from Ben and also Victor's group and published at ICAPS this year. So very fresh work. So as Victor mentioned, that there are benefits of using multiple proposal. And then in this case, so we can basically construct a proposal as a mixture of Gaussian. And for each Gaussian, the mean and also covariance can be constructed using neural networks. And then you can basically choose, well, what is a component or which component of the Gaussian mixture you should use to construct the proposal. There are different ways to do that, and then to make it differentiable, you can also use tricks like Gumbel softmax to do that. So that is also another direction to construct proposal distribution using neural network. But in this case, just a mixture of Gaussian with a mean and covariance decided by some neural networks that we can learn. Yeah, I think that is perhaps where I can stop before we go to the next part. Let's go. Thank you. Ask questions and. Sure.
You can make a particle sample. No reason you can't, because of your particle sampler that can be written as a function.
You use